What if I told you the most powerful diesel engine ever sold in America wasn't a Detroit, and that it was sitting right there for anyone to buy? But almost nobody did. By the late 1980s, there was an engine available that made Detroit Diesel's celebrated new model look modest by comparison. This wasn't some exotic prototype or a limited-run experiment. It was a production engine, ready to work, available to anyone who wanted it. And it was more powerful. Significantly more powerful. While the entire trucking industry held its breath waiting for Detroit's revolutionary new Inline 6, the one that was supposed to save American trucking, this other engine was already here, already proven, already available. But here's the thing. It didn't matter. Within a few years, it had quietly vanished from the American market. Not because it failed, not because it broke down, it just faded away. Today, most truckers have never even heard of it. So what happened? How does the strongest, most capable Inline 6 diesel available at the time get completely erased from trucking history? The answer reveals why raw power has never been enough to win in American trucking. By the mid-1980s, American heavy-duty trucking faced a problem nobody wanted to talk about openly. The engines powering the nation's freight were fundamentally outdated. Detroit Diesel was still selling two-stroke engines that traced their basic architecture back to World War II. Cummins was offering updated versions of the Big Cam, a design from the 1970s. Caterpillar's mechanical 3406 had proven reliable, but it was aging fast. All of these engines were loud, prone to oil leaks, and increasingly difficult to tune for the emission standards that kept getting stricter. Fleet managers faced mounting pressure from every direction. Fuel costs were climbing. Environmental regulations were tightening. Drivers were demanding more comfortable, quieter trucks. And the existing engines simply weren't built to meet all three demands at once. The industry needed something fundamentally different. Not just an improved version of what already existed, but a clean sheet design that could handle modern demands while lasting long enough to justify the investment. Detroit Diesel understood this better than anyone. They'd built their reputation on two-stroke engines, the famous Screamin' Jimmy sound that defined American trucking for decades. But by 1987, even Detroit's engineers knew that architecture had reached its limits. The two-stroke design was inherently inefficient, burned too much oil, and produced emissions that were becoming impossible to control. Their answer arrived in 1987, though it wouldn't reach production until 1988. The Series 60 represented Detroit's first four-stroke engine, and their first attempt to build a completely electronic diesel from the ground up. The timing mattered. Detroit wasn't just introducing a new engine. They were betting the entire company on a radical departure from everything they'd ever built. The Detroit Diesel Series 60 looked conventional enough from the outside, a standard inline 6 configuration that fit into existing truck chassis without major modifications. But beneath that familiar shape sat technology that no American manufacturer had successfully mass-produced before. Every aspect of the Series 60's operation ran through Detroit's new electronic control system, which they called DDEC, Detroit Diesel Electronic Control. The system monitored and adjusted fuel injection timing, throttle response, and engine parameters continuously, making thousands of calculations per second. For the first time, an engine could diagnose its own problems and tell mechanics exactly what was failing instead of forcing them to guess. This wasn't just convenient, it transformed how fleets managed maintenance. DDEC stored fault codes that could be read with diagnostic tools. It tracked driver behavior, recorded hard accelerations and excessive idling, and provided data that helped fleet managers improve fuel economy across their entire operation. The system could even limit top speed or torque output, giving fleet operators unprecedented control over how their trucks were driven. But the real breakthrough was reliability. Early Series 60 engines produced between 330 and 365 horsepower, respectable numbers, but not groundbreaking. What mattered was that they delivered that power consistently day after day, with far less maintenance than the engines they replaced. Operators who switched from older Detroit two-strokes or mechanical Cummins engines reported fuel economy improvements of half a mile per gallon or more. That might not sound dramatic, but for a truck running 100,000 miles per year, it meant thousands of dollars in annual savings. The Series 60 ran quieter, produced less visible smoke, and didn't require the constant adjustments that mechanical injection pumps demanded. The engine's design reflected lessons Detroit had learned from decades of field experience. The block was deep-skirt cast iron, rigid enough to handle high cylinder pressures without flexing. The cylinder head used 4 valves per cylinder, a layout that improved breathing and combustion efficiency compared to the 2-valve designs still common in American trucks. The overhead camshaft design reduced valve train complexity and improved durability at high mileage. Detroit had also solved one of the biggest problems that plagued earlier electronic engines: calibration. Many early attempts at electronic diesel control suffered from rough idle, surging under load, or poor throttle response. The Series 60 felt smooth and predictable from the first production units. Drivers didn't need to adapt their technique. The engine simply worked the way they expected it to. By 1990, the Series 60 had become the default choice for long-haul fleets across America. Production ramped up quickly, and within a few years, Detroit had captured a dominant share of the Class 8 market. The engine would eventually be offered in ratings up to 500 horsepower and beyond. But even the early versions established a reputation that competitors struggled to match. Fleet mechanics appreciated how the engine was laid out. Components were accessible. Routine maintenance took less time than on older engines, and most importantly, parts were available everywhere. Detroit had built one of the largest service networks in North America, and the Series 60 plugged directly into that infrastructure. A truck could break down almost anywhere in the continental US and find a dealer who stocked parts and employed technicians who knew the engine intimately. That combination, reliable performance, nationwide support, and proven fuel economy, created a feedback loop that made the Series 60 almost impossible for competitors to displace. Fleets trusted it because other fleets trusted it. Drivers liked it because they knew they could get help if something went wrong. And mechanics preferred working on it because the diagnostic system eliminated most of the guesswork that made older engines frustrating to repair. By the early 1990s, the Series 60 had achieved something rare in industrial equipment. It had become the standard by which everything else was measured. But while American fleets were locking on to the Series 60 as the obvious choice, another manufacturer had already built an inline 6 that pushed diesel performance into an entirely different category. Volvo had been building heavy trucks in Sweden since 1928. But by the 1980s, the company had developed a reputation for engineering that prioritized durability over flash. Their trucks weren't the prettiest machines on European highways, but operators who ran them in harsh conditions, timber hauling through Norwegian mountains, long-distance freight across Swedish winters, knew they could depend on them. The engine that best exemplified Volvo's approach was the TD 162, introduced in the mid-1980s as the flagship power plant for their heaviest trucks. The designation came from its displacement, 16.2 liters, making it one of the largest inline-6 diesels in production anywhere in the world. To understand just how massive that was, consider that the Detroit Series 60 displaced 12.7 liters. The Cummins N14, which wouldn't arrive until 1988, displaced 14 liters. The TD 162 dwarfed both of them, and it had been in production for years before any American engine reached the market. Volvo didn't build the TD 162 to compete in the American long-haul market. They built it for conditions that American trucking rarely encountered: extreme grades, brutal weather, and gross vehicle weights that would send a DOT inspector into shock. Scandinavian timber trucks routinely operated at 60 tons, over 130,000 pounds. Australian road trains, which became some of the TD162's biggest customers, ran triple trailer combinations at weights approaching 300,000 pounds. The engine had to handle sustained full-load operation for hours at a time, without overheating, losing power, or shaking itself apart. Volvo's solution was straightforward. Overbuild everything. The crankshaft was forged steel, among the heaviest in any production inline-six of the era. The main bearing journals were massive, spreading loads across a wider surface area to prevent the fatigue cracks that killed lesser engines under constant stress. The block carried extra material in the main webs and deck, not to save weight, but to resist distortion when cylinder pressures peaked and temperatures climbed. Even in street-legal configurations, the TD162 produced over 550 horsepower by the late 1980s, at a time when a strong American truck engine was making 400, but the raw horsepower number only told part of the story. The torque curve was what separated the TD162 from everything else on the road. European heavy-haul work rewards engines that pull from low RPM and stay planted instead of dropping off the moment a grade steepens. Volvo tuned the TD162 to deliver thick, sustained torque starting around 1,000 RPM and holding nearly flat through the middle of the rev range. Drivers didn't need to downshift constantly to stay in the power band. They could hold a gear and let the engine work. Logging operators in Scandinavia noticed this immediately. When pulling a fully loaded timber trailer up a steep mountain grade on ice, losing momentum meant the entire rig could slide backward. The TD162's ability to maintain pulling force without surging or hesitating made it the preferred choice for work, where engine behavior was a safety issue, not just a convenience. The fuel system contributed to that smoothness. Volvo used mechanical injection with precisely profiled cam lobes that delivered consistent fueling even under extreme load. Drivers who ran these engines in the Australian interior, where ambient temperatures could exceed 110 degrees Fahrenheit, reported that the TD162 didn't fade the way some American engines did. It held its power, kept its temperatures stable, and didn't punish drivers with unpredictable boost behavior on long climbs. The cold weather performance was equally impressive. In northern Sweden, where winter temperatures routinely dropped below -20 Fahrenheit, the TD162 reached operating temperature quickly and maintained oil pressure reliably. Volvo's engineers had intentionally oversized the oil passages and designed the cooling system with enough reserve capacity to handle both Arctic cold and desert heat. The engine's adaptability to temperature extremes was a major factor in its popularity across climates that had nothing in common except their hostility to machinery. Another detail that mattered in constant load applications was durability. The TD162's connecting rods were long relative to the stroke, which reduced side loading on the cylinder walls and increased piston lifespan. The bearings were wider than necessary by American standards, spreading forces more evenly. The pistons were forged aluminum reinforced with steel inserts, a design choice that added weight but tolerated abuse that would have cracked lighter castings. Operators who rebuilt these engines after hundreds of thousands of miles frequently noted that the bottom ends stayed in excellent condition. Bearings showed normal wear patterns instead of the scoring and discoloration that indicated oil starvation or overheating. Cylinder walls remained within tolerance. The engine was simply built to survive the kind of duty cycles that destroyed weaker designs. In Europe and Australia, the TD162 earned a loyal following among operators who needed an engine that could take punishment and keep working. It wasn't marketed as the most efficient choice or the quietest option. It was marketed as the engine you bought when failure wasn't acceptable. And here's the surprising part: it was available in the United States. Volvo began selling heavy trucks in North America during the 1980s, initially through a partnership with White Motor Company, and later under its own brand after acquiring White's truck division. The TD162 was quietly offered as a power option in select models, primarily vocational trucks aimed at construction, logging, and heavy hauling. These weren't over-the-road tractors meant for cross-country freight. They were purpose-built machines for operators who needed maximum pulling power and didn't care where the engine came from as long as it worked. A small number of TD162-powered Volvo and White GMC trucks made it onto American highways and job sites during the late 1980s and early 1990s. But the engine never gained traction. Most American fleets had never heard of it, and the few who had weren't interested. The reasons reveal how the trucking industry actually makes decisions and why raw performance numbers matter less than most people assume. The first problem was infrastructure. By 1990, Detroit Diesel had hundreds of authorized service centers across the United States. Parts for the Series 60 were stocked everywhere from Los Angeles to rural Nebraska. If a Series 60 powered truck broke down, it could usually be fixed the same day or within a few hours. The downtime was predictable, and predictable downtime was manageable. Volvo's dealer network was far smaller. In many parts of the country, the nearest Volvo truck dealer was hundreds of miles away. If a TD162 went down, a fleet might wait days for a part to arrive, or for a technician who actually knew the engine. That uncertainty alone was enough to make most fleet managers pass, regardless of how good the engine was mechanically. The second barrier was cultural. American trucking in the 1980s had a strong preference for domestic manufacturers. Fleets had decades of experience with Detroit, Cummins, and Caterpillar. They understood how those companies operated, how to negotiate pricing, and how to manage warranty claims. Buying a Volvo engine meant dealing with a European manufacturer that operated differently, used metric specifications, and didn't share the same service philosophy as American companies. Even independent owner-operators, who theoretically had more freedom to choose equipment, were reluctant to take a chance on an unfamiliar brand. Resale value mattered, and trucks with well-known American engines held their value better. A Freightliner with a Series 60 or a Kenworth with a big cam would find a buyer quickly. A Volvo with a TD162 might sit on a dealer lot for months. Cost was another factor. Volvo trucks equipped with the TD162 were more expensive than comparable American trucks with domestic engines. For fleets buying dozens or hundreds of units at a time, even a few $1,000s per truck added up fast. And because Volvo didn't have the manufacturing scale of its American competitors, it couldn't bring prices down to match. But the biggest obstacle was that most American fleets simply didn't need what the TD162 offered. The engine was designed for conditions that were rare in the United States. American trucks operated under a federal gross vehicle weight limit of 80,000 pounds. Most long-haul routes ran across relatively flat interstate highways at steady speeds. Fuel efficiency mattered more than brute power. The Series 60's 365 horsepower and superior fuel economy made perfect sense for that kind of work. The TD162's 550 horsepower was overkill. It solved a problem that American fleets didn't have. The extra power didn't translate into faster delivery times or lower operating costs. It just burned more fuel. There were niche applications where the TD162 excelled. Heavy haul operators moving oversized loads appreciated the extra torque. Logging companies in the Pacific Northwest, where steep grades and heavy weights were common, found the engine well suited to their work. But these were small segments of the market, not large enough to support widespread adoption. Volvo never aggressively marketed the TD162 in the United States the way Detroit promoted the Series 60. The engine was simply listed as an available option in vocational truck specifications, without much fanfare. Volvo's marketing focused on the overall truck, build quality, safety features, and long-term durability, rather than highlighting the engine as a performance flagship. As a result, the TD-162 remained nearly invisible in American trucking. The few operators who bought them often ran them until the rest of the truck failed, because the engines themselves almost always outlasted everything around them. But those successes happened quietly, without generating the kind of buzz that could shift industry opinion. By the mid-1990s, Volvo had moved on to newer engine designs that met stricter emission standards and offered better fuel economy. The TD-162 was phased out, replaced by more modern architectures that were easier to certify and more appealing to cost-conscious fleets. In the end, the TD-162 never failed because it wasn't good enough. It failed because it didn't fit the American trucking environment. Fleets weren't looking for the strongest engine. They were looking for the one that simplified their operations, and the Series 60 did that better than anything else available. While American fleets ignored the TD-162, operators in other parts of the world built entire businesses around it. In Scandinavia, the engine became standard equipment for timber haulers. These operations ran trucks at gross weights exceeding 60 tons through terrain that combined steep grades, tight switchbacks, and seasonal ice. Losing momentum on a climb meant stopping completely, and getting a fully loaded timber truck moving again from a standstill on a grade was nearly impossible. The torque curve on the TD-162 made it the ideal tool for this work. Drivers could hold a gear and maintain speed without the engine dropping off or surging. The consistent power delivery reduced driver fatigue on long mountain routes and improved safety by eliminating the unpredictable behavior that plagued lesser engines under load. Norwegian operators in particular praised the engine's cold weather reliability. Starting a diesel engine at -30 Fahrenheit is difficult under the best circumstances, but the TD-162's robust construction and well-designed fuel system made it one of the more dependable options in Arctic conditions. Glow plugs worked effectively, the injection system maintained pressure, and the engine reached operating temperature quickly enough to keep cab heaters functional. Australia pushed the TD-162 even harder. Road train operators in the Outback ran triple trailer combinations at gross weights approaching 300,000 pounds, more than 3 times the legal limit in the United States. These rigs hauled ore, livestock, and freight across distances that dwarfed anything in North America, often traveling hundreds of miles between towns on roads that barely qualified as paved. The environment was brutal. Daytime temperatures exceeded 110 degrees Fahrenheit. Dust infiltrated every mechanical system. Corrugations in the road surface generated vibrations that loosened bolts and cracked welds. And if an engine failed in the middle of the Outback, the nearest repair facility might be 8 hours away. The TD-162 proved itself in those conditions by simply refusing to die. Operators reported engines running 500,000 miles or more with only routine maintenance, oil changes, filter replacements, and occasional injector servicing. The engine's oversized cooling system handled the heat without complaint. The robust internal components tolerated the constant vibration, and the mechanical injection system, while less sophisticated than modern electronics, was nearly immune to the dust and electrical gremlins that plagued more complex designs. Road train drivers developed a deep respect for the TD-162's ability to maintain power in extreme heat. Some American engines would begin derating, automatically reducing power output to prevent overheating, when ambient temperatures climbed above 100 degrees. The TD-162 held its rated output even in 115-degree heat, with a fully loaded rig climbing a long grade. That reliability was the difference between completing a delivery on schedule and sitting stranded while the engine cooled. The transmission pairings common in these applications also played to its strengths. Many Volvo F-16 trucks equipped with the engine ran heavy-duty manual gearboxes, with close ratio gearing optimized for climbing rather than cruising. These setups gave drivers fine control over engine speed and load, allowing them to keep the engine in its optimal torquey range regardless of terrain. In contrast, American trucks typically use transmissions with wider gear spacing and taller overdrive ratios, designed for efficient highway cruising. The Series 60 worked beautifully with those transmissions on flat interstates, but the TD162's setup was built for mountains and grades, environments where American long-haul trucks rarely operated. European long-distance operators also appreciated its durability and sustained load work. Unlike American trucking, where speeds were often limited by regulations and traffic, European trucks frequently ran at or near maximum speed for hours at a time on unrestricted highways. Its internals, long connecting rods, oversized bearings, and reinforced pistons were designed to handle that kind of continuous, high-output operation without accelerated wear. Rebuild intervals reflected this durability. Many TD162 engines ran 800,000 miles or more before requiring major overhauls, intervals that were considered exceptional even for the best American engines of the era. And when rebuilds were performed, technicians often found that the bottom end remained in excellent condition, showing normal wear patterns rather than the scoring, cracking, or distortion that indicated systemic problems. The engine's reputation spread through word of mouth among operators who worked in demanding conditions. A Finnish logging contractor would hear from a Norwegian colleague about how well the TD162 handled mountain work. An Australian road train operator would recommend it to another hauler based on personal experience in the Outback. These endorsements carried more weight than any marketing campaign because they came from people who depended on the equipment to make a living. The engine was building this reputation overseas. Back in the United States, it remained almost completely unknown. The few American operators who ran them were typically in niche industries, heavy construction, logging, specialized hauling, and they rarely talked publicly about their equipment choices. The engine's successes happened quietly, in places most American truckers never saw. The TD162 story reveals something important about how industrial equipment markets actually work. The best performing product doesn't always win. Sometimes the product that wins is simply the one that fits most easily into the existing system. The Series 60 dominated American trucking not because it was the most powerful engine available, it wasn't, but because it solved the specific problems American fleets cared about most. It was fuel efficient, reliable, well-supported, and familiar. It didn't require fleets to change how they operated, retrain their mechanics, or build new parts inventories. It simply worked, and it worked within the infrastructure that already existed. The TD162 required American fleets to do all the things they didn't want to do. It meant dealing with a foreign manufacturer. It meant finding technicians who understood metric specifications and European design philosophy. It meant accepting higher fuel consumption in exchange for power that most fleets would never use. And it meant taking a risk on a product that had almost no track record in the American market. Fleet managers aren't paid to take risks. They're paid to keep trucks running and costs predictable. The Series 60 was the safe choice, and in trucking, the safe choice is usually the right choice. But there's another lesson here. The TD162's success in Scandinavia and Australia shows that context matters more than raw specifications. An engine that was overkill in the United States was essential in other parts of the world. The same machine that American fleets dismissed as too powerful and too expensive became the backbone of heavy haul operations in environments where anything less would have failed. This isn't unique to diesel engines. It's a pattern that repeats across industrial equipment. The most capable machine isn't always the most successful. The machine that succeeds is the one that matches the specific needs, expectations, and limitations of the market it enters. The TD162 never had a real chance in American trucking because it was solving the wrong problems. American fleets didn't need an engine that could pull 300,000 pounds up a mountain in 110-degree heat. They needed an engine that could run 500,000 miles between overhauls while delivering 6 miles per gallon on flat interstates. Detroit Diesel understood that, and they built the Series 60 accordingly. Volvo built the TD162 for a different world, a world of extreme terrain, massive loads, and conditions that would destroy lesser engines. In that world, the TD162 was exactly what operators needed. But that world wasn't America. Today, finding a TD162 on American roads is nearly impossible. The few that were sold here have either been scrapped, exported, or are sitting in the back corners of small fleets where they continue to do the work they were built for. In Australia, some are still running. Road train operators who bought Volvo F-16 trucks in the late 1980s have kept them in service for decades, rebuilding the engines when necessary, but never replacing them. The TD162 has become something of a legend in the Australian heavy haul community, an engine that represents a time when manufacturers built equipment to survive rather than to meet price points. In Scandinavia, most have been retired, replaced by newer engines that meet modern emission standards. But operators who ran them still speak highly of the TD162's capabilities. It wasn't the most sophisticated engine, and it certainly wasn't the cleanest or quietest, but it was strong, simple, and nearly indestructible. The irony is that the TD162 was more powerful, more durable, and more capable than the engine that became the standard in American trucking. But none of that mattered, because American trucking didn't value those qualities as highly as it valued parts availability, fuel economy, and ease of service. The Series 60 won because it understood what mattered most to its customers. The TD162 lost because it didn't. That's not a failure of engineering. It's just the reality of how markets work. If you've ever driven a truck with a TD162, or if you know someone who ran one in the States, share your story in the comments. These engines deserve to be remembered, even if the industry they were built for never gave them a chance.